Few of us likely spend much time thinking about our bones, yet this intricate framework is as impressive as any architectural marvel. The human skeleton, a masterpiece of natural engineering, provides the structural foundation upon which our bodies are built. Composed of 206 individual bones in adulthood, this living scaffold supports our weight, allows for movement, and protects our vital organs. Bones are much more than just rigid structures. They are living tissues, constantly remodeling and adapting to our body's needs. Within their hard exterior lies a complex world of cells, blood vessels, and minerals, all working in concert to maintain our health and well-being. Our bones serve as a reservoir for essential minerals, play a crucial role in blood cell production, and even influence our metabolism. Each bone, from the delicate bones in our inner ear to the sturdy femur in our thigh, has a specific shape and function, perfectly adapted to its role in the body. The intricate connections between bones, formed by joints, ligaments, and tendons, allow for a remarkable range of motion, from the delicate movements of a pianist's fingers to the powerful strides of a marathon runner. Bones are often perceived as inert and lifeless, but nothing could be further from the truth. They are living, dynamic tissues, constantly changing and adapting to the body's needs. Bones are composed of specialized cells called osteoblasts, osteocytes, and osteoclasts, each with a specific role in bone formation, maintenance, and remodeling. Osteoblasts are the master builders, responsible for producing new bone tissue. As bone tissue matures, some osteoblasts become trapped within the matrix, transforming into osteocytes. Osteocytes, the most abundant cells in bone, reside within small spaces called lacunae. They act as sensors, detecting mechanical stress and microdamage within the bone. Osteoclasts, on the other hand, are responsible for bone resorption, releasing minerals into the bloodstream as needed. The coordinated action of osteoblasts and osteoclasts ensures that bones remain strong and healthy throughout life. The skeletal system provides a rigid framework that supports our body weight, allowing us to stand upright and move with ease. Bones act as levers, working in conjunction with muscles and tendons to produce movement. Muscles contract, pulling on tendons, which in turn exert force on bones, causing them to move at the joints. The skull, a complex structure composed of multiple fused bones, encases and safeguards the brain, our body's most vital organ. The rib cage, a bony cage formed by the ribs and sternum, protects the heart and lungs, essential organs for circulation and respiration. The vertebral column, or spine, provides support and protection for the spinal cord, a vital communication pathway between the brain and the rest of the body. The pelvic bones shield the reproductive organs and urinary bladder. Even the delicate bones of the middle ear serve a protective function, transmitting sound vibrations to the inner ear while shielding it from loud noises. The skeletal system, therefore, not only provides structural support, but also acts as a silent guardian, safeguarding our most vital organs from external forces. The human skeleton is composed of two main types of bone tissue, compact bone and spongy bone. Compact bone, as its name suggests, is dense and hard, forming the outer layer of most bones. It provides strength and rigidity, resisting bending and compression forces. Spongy bone, also known as cancellous bone, is found within the interior of bones. It has a porous, honeycomb-like structure, which makes it lighter than compact bone. This intricate network of bony trabeculae provides strength while minimizing weight, allowing for efficient movement. The distribution of compact and spongy bone varies depending on the bone's function. Bones subjected to high stress, such as the femur and the thigh, have a thicker layer of compact bone to withstand the forces of weight bearing. Within the cavities of some bones, particularly the long bones of the arms and legs, lies bone marrow, a soft gelatinous tissue responsible for hematopoiesis, the production of blood cells. Beyond their structural and protective roles, bones serve as a vital reservoir for essential minerals, particularly calcium and phosphate. Calcium is crucial for a wide range of bodily functions, including muscle contraction, nerve impulse transmission, blood clotting, and enzyme activity. Phosphate is essential for energy production, DNA and RNA synthesis, and cell signaling. Bones store approximately 99% of the body's calcium and 85% of its phosphate. This mineral reserve is constantly being deposited and withdrawn, depending on the body's needs. When blood calcium levels drop, specialized cells in the parathyroid glands release parathyroid hormone, or PTH. PTH stimulates osteoclasts to break down bone tissue, releasing calcium into the bloodstream. Conversely, when blood calcium levels rise, the hormone calcitonin, produced by the thyroid gland, inhibits bone resorption and promotes calcium deposition in bones. Deep within the cavities of certain bones lies a remarkable tissue known as bone marrow. This soft, gelatinous substance is responsible for hematopoiesis, the production of all the different types of blood cells our bodies need to function. Hematopoiesis is essential for life, as blood cells are responsible for transporting oxygen, fighting infections, and clotting blood. Red bone marrow, found in the spongy bone of the skull, ribs, sternum, vertebrae, pelvis, and the ends of long bones, is the primary site of hematopoiesis in adults. Within this specialized environment, hematopoietic stem cells, the precursors to all blood cells, undergo a remarkable process of differentiation and maturation. Driven by a complex interplay of growth factors and signaling molecules, these stem cells give rise to red blood cells, white blood cells, and platelets. Red blood cells, packed with the oxygen-carrying protein hemoglobin, transport oxygen from the lungs to the body's tissues. White blood cells, the body's immune cells, defend against infection and disease. The human skeleton undergoes a remarkable transformation from the moment we are born to the time we reach adulthood. At birth, our skeletons are composed mostly of cartilage, a tough but flexible tissue. Cartilage provides a framework for bone development and allows for the rapid growth that occurs during infancy and childhood. As we grow, a process called ossification gradually replaces cartilage with bone tissue. Ossification begins at specific points in the cartilage called ossification centers. Osteoblasts, the bone-building cells, migrate to these centers and begin depositing a matrix of collagen and minerals. This process continues throughout childhood and adolescence, with bones increasing in length and width. Long bones, such as the femur and humerus, grow in length at specialized areas called growth plates, located near the ends of the bones. Bone growth is regulated by a complex interplay of hormones, growth factors, and mechanical forces. Despite their strength and resilience, bones are susceptible to injury, just like any other part of the body. Fractures or broken bones are common injuries that can occur from a variety of causes, including falls, sports injuries, and motor vehicle accidents. Fortunately, bones have a remarkable capacity for self-repair. When a bone fractures, the body initiates a complex healing process to repair the damage. The first stage involves the formation of a blood clot at the fracture site. This clot helps stabilize the fracture and provides a framework for new bone formation. Next, a soft callus, composed of fibrous tissue and cartilage, forms around the fracture. The soft callus acts as a temporary splint, holding the broken ends of the bone together. Gradually, the soft callus is replaced by a hard callus made of new bone tissue. The human skeleton is a testament to the incredible durability and resilience of our bodies. Bones can withstand remarkable forces, protecting our vital organs and allowing us to move with strength and agility. But the lifespan of a bone cell is relatively short, ranging from a few weeks to a few months. Throughout our lives, our skeletons are constantly being remodeled, with old bone tissue being broken down and replaced by new bone. This continuous process of bone remodeling ensures that our bones remain strong and healthy, adapting to our changing needs. Factors such as exercise, nutrition, and hormone levels all influence the rate of bone remodeling. Regular weight-bearing exercise, for example, stimulates bone formation, increasing bone density and strength. A diet rich in calcium and vitamin D is essential for providing the building blocks for new bone tissue. As we age, however, bone remodeling often becomes imbalanced, with bone resorption outpacing bone formation, leading to a decrease in bone density and increasing the risk of osteoporosis. From the intricate structure of a single bone cell to the remarkable complexity of the entire skeletal system, our bones are a testament to the wonders of human biology. They provide the scaffolding upon which our bodies are built, protect our vital organs, and allow us to move with grace and precision. But bones are much more than just structural elements. They are living, dynamic tissues, constantly adapting to our body's needs. The next time you marvel at the beauty of a sculpture or the elegance of a building, take a moment to appreciate the architectural wonder within your own body. Your skeletal system, a masterpiece of natural engineering, is a testament to the intricate beauty and remarkable resilience of life.